Friction coefficients in conduits on channels. Chézy, Darcy, Gauckler-Manning, Strickler, Weisbach coefficient. In pipes and conduits, the friction losses are traditionally expressed in the form of energy loss, with the energy loss being proportional to the friction coefficient times the length of the pipeline over the diameter times the square of the velocity. And here, with this diagram, delta H will represent the regular head loss, and dH the equivalent pipe diameter. The total head, H, expressed in meter of water, is the total energy per unit mass. The velocity, in a pipeline, is equal to the ratio of the volume flow rate to the cross-section area, while the equivalent pipe diameter is equal to 4 times the cross-section area over the weighted perimeter. For a rectangular pipe, this equivalent pipe diameter equals the pipe diameter, and the ratio of the cross-section area to the weighted perimeter is sometimes referred to as a shape factor. The Darcy-Weisbach friction factor F is linked to the boundary shear stress, tau naught, averaged over the weighted perimeter, PW, with the boundary shear stress being equal to F over A times rho V squared with rho the fluid density. Fundamentally, the Darcy-Weisbach friction factor F is a dimensionless boundary shear stress. For steady Newtonian incompressible fluid flow, dimensional consideration shows that the Darcy-Weisbach friction coefficient is a function of the Reynolds number on relative roughness height, with the Reynolds number defined in terms of the cross-sectional average velocity V on equivalent pipe diameter dH, with mu the fluid viscosity, while the relative roughness height is the ratio of the equivalent sound roughness height of the conduit boundary to the equivalent pipe diameter. The Darcy-Weisbach friction factor may be estimated graphically from the Moody diagram. The Moody diagram, which is based upon extensive dataset including some recent superpipe data, and it covers both laminar and turbulent flow for relative roughness up to 5%. It is valid in steady Newtonian fluid flow, and it is applicable and validated for both pipe and open channel flow. One may refer to a video movies in this channel. This diagram illustrates the Moody diagram with the Darcy-Weisbach friction factor on the left vertical axis, the Reynolds number as the horizontal axis, and the relative roughness height as on the right vertical axis. On the same graph, we have highlighted the region corresponding to laminar flow motion and turbulent flow motion. Ancient and old studies of flow resistance investigated the relationship between discharge, energy slope, and surface resistance. Most were undertaken in open channels of various shapes, and a few empirical formulas are still used today in the industry: the Chézy equation, the Gauckler-Manning equation, and the Strickler equation, in which SF is the longitudinal slope of the total energy line. One would note that empirical friction coefficients are not dimensionless with their unit shown in this table, comparing the equivalent sound roughness height of well-known material with typical quantitative and dimensional values of these empirical coefficients. Through the mid-19th century to 20th century, these empirical formulae were applied assuming a constant friction coefficient, irrespective of the relative roughness height and channel shape. This assumption is fundamentally flawed and can lead to physically meaningless results. Furthermore, most empirical friction coefficients are dimensional, not dimensionless, with implicit limitation when we want to extrapolate upscale physical data, not to mention human errors during the conversion between systems of units. This table here illustrates the expression of the velocity and boundary shear stress as a function of the Darcy-Weisbach friction factor, which is the most correct way to approach the problem, and shown also for comparison when one uses Chézy, Gauckler-Manning, or Strickler friction coefficients. Flow resistance in pipes and open channels was historically estimated using empirical formulae and empirical friction coefficient because of a lack of understanding of the flow physics. In modern times, many scholars and learning societies argue that this outdated and physically meaningless concept are not promoting the fundamental of fluid mechanics in engineering applications, and that the preceding development in terms of the Darcy-Weisbach friction coefficient offer a most rigorous way of the problem of flow resistance. A few quotes. The Chézy and Gauckler-Manning equation express our continuing ignorance of turbulent process. Their use for man-made channel is highly inaccurate. They are best empirical relationship with scarcely a trace of analytical foundation. There is a great utility in expressing resistance to steady, fully developed flow in uniform channel in terms of the Darcy friction factor F. The problem of determination of head loss is a question of physics. In summary, with man-made conduits and channels, the flow velocity, regular energy losses, and boundary shear stress must be calculated in terms of the Darcy-Weisbach friction coefficient, with the expression here for the velocity, head loss, and boundary shear stress. Two examples of man-made conduits and channel used to transport water supply are shown here. The Mount Crosby pipeline at Ansted in March 2024, and the second photograph of an aqueduct linking Toyohashi to Tahara in Japan, photograph taken in 1999. The calculations of friction losses in conduits and channels constitute a fundamental application of the equation of conservation of mass and energy in pipes and open channels, most relevant to many hydraulic engineering applications. This is further discussed in a number of relevant YouTube video movies in the same YouTube channel.